Okay, we're almost done with chapter 3. We're at section 3.10. And I don't know why they introduced this far in to the term, but we're going to balance chemical reactions. We've been seeing them all along. But we're going to look at them now and then utilize this information to get more complicated in terms of our calculations in chapter 4 on really how much ingredients do we need to throw into a reaction vessel in order to make a certain amount of products. We're going to get really detailed in chapter 4. So a chemical equation, of course, is a representation. It's basically a recipe. And so what we'll look at is the reactants are the starting materials. They're always found to the left-hand side of the arrow. And the products are always written on the right-hand side of the arrow. And they are, of course, what we make in a chemical reaction. And so how to read a chemical equation is the coefficients out front are mole-to-mole ratios. So 2 moles of aluminum plus throwing in 3 moles of bromine as a liquid. The solid here, S means a solid. These are the states of matter found inside the parentheses. We have bromine as a liquid, and we're going to make aluminum bromide as a solid. Okay, and so it will tell us the states of matter. And so 3 moles of bromine as a liquid makes 1 mole of aluminum bromide as a solid. Now, we could also look smaller. These coefficients could be 2 atoms of aluminum and 3 molecules of bromine. Now, hopefully you can answer why we use the word atoms with aluminum and molecules with bromine. Can you? Can you answer that? The aluminum is an element, and so the smallest indivisible unit of an element is an atom. Br2, there are 2 bromines bonded together. So it is not one element all by itself. It's a molecule. The smallest individual unit is called a molecule, not an atom. An atom is all by itself. Now, aluminum bromide is not a molecule. It is a metal with a nonmetal, and so we say the smallest indivisible unit of a compound, such as this, is called a formula unit. Confused yet? So molecules are nonmetals bonded with other nonmetals, so the smallest unit of a nonmetal bonded to another nonmetal is a molecule. The smallest unit of an element is an atom. The smallest unit of a compound, typically a metal and a nonmetal, is called a formula unit. It is not 2 grams of aluminum plus 3 grams of bromine make 1 gram of aluminum bromide. And hopefully from chapter 2 you'll see this can't be true because the mass conservation, 2 plus 3 is 5. Okay? And so it would not equal 1 gram of the product. We got to get at least 5 grams. Mass conservation. So we can talk about the number of atoms of each type of element. And so what we'll find is atoms on both sides of the balanced equation have to be equal. If we have 5 atoms of carbon on the left, we must have 5 atoms of carbon on the right. Subscripts cannot be changed to balance an equation. And the balanced equation will tell us the ratio, the number of molecules that need to react with each other. You need 4 cups of flour, 1 bag of chocolate chips, 2 eggs to make 1 batch of cookies. That's what it's telling us. And then our coefficients out front can be fractions, but they're usually given as the lowest integer multiples. And that's going to be key in mastering. When you're balancing an equation, make sure those coefficients out front are the lowest integer multiples. Okay, so if you have like 2a plus 4b makes 2c, these are not the smallest integer values. We can reduce that to a plus 2b makes a c, because we can divide each of these coefficients by 2 and make them smaller. So we reduced it. So when we're putting this into mastering, 1a and 2b's make 1c. Okay? So if we're going to balance an equation, what I'm going to do is I'm going to show you how to do this. First of all, I always pick the most complicated molecule on the left, and I start trying to balance all the elements. I never balance oxygens or hydrogens until the end if I can. And so I'm going to kind of give you some hints on how to do this. Okay, and so I'll show you painstakingly how to balance some equations here. And again, it takes practice. If it takes you 10 minutes to balance a chemical reaction, you'll never finish a problem. And in chapter 4, balancing a chemical reaction may be only worth 4 points out of a 30-point problem. And so you need to be able to balance a chemical reaction in 2 minutes or less for a really hard one, 1 minute or less for a really easy one. Because you have to have your recipe to be able to go on and figure out how much product you're going to make, how many millions of sticky Post-it notes are you going to make for 3M, given 4 truckloads of tree sap, you know. So your boss will say, how much product are you going to make? And so we got to know that. So I've got 1 carbon here, and the subscript under the 2 means there's 2 sulfurs. So if I look over here, there's 1 carbon over here, but there is only 1 sulfur, okay, because there's no subscript there. So I'm going to only use coefficients written out in front of the molecules. I'm not going to change the subscripts. So if I put a 2 in front, it means I want 2 of these SO2 molecules to react. The 2, it means the same thing as writing this down 2 times. So there's 1 sulfur here and 1 sulfur here for a total of 2. Now that's balanced. Now I have 2 oxygens on this side, and I have 2 here and 2 here for a total of 4 oxygens on this side. So I want the 2 oxygens on this side to be the same as 4. So if I write a 2 out in front, I'm going to get 2 oxygens on this side. Oh, I just messed that up. Let's take an eraser here, because this is easy to do. And get our pen back. Let's go back to the right-hand side. There are 2 oxygens in CO2, but there is 2 times the oxygens in SO2. So if we were to write that down twice, there's 2 here and 2 here for 4. So if I take the 2 times the subscript, the 2 out front, and multiply it through all the subscripts, so the subscript for S is 1, so 2 sulfurs, 2 times the 2 subscript for oxygens, I get 4 oxygens in SO2, okay? Because there's 2 SO2 molecules, so 2 plus 2 is 4. So that equals 6 oxygens on the right-hand side. Whoops. So I have 2 on the left. So if I take 3 times the subscript of 2, or if I just wrote the O2s out 3 times, then 3 and 2 plus 2 plus 2 is 6. So I have 6 O's on this side. So bam, she's balanced. So here is the balanced chemical reaction. I have the same number of atoms of each of the elements on both sides of the equation. So let's look at another example. This is the most complicated, so I'm going to start with this guy first. I have 1 nitrogen on this side, 1 nitrogen on this side. So I'm going to just say 1N, 1N. I have 3 hydrogens on this side. On this side, there are only 2 hydrogens. So the 3 and the 2, we can't just double one of them and get the other number. They both go into 6. So I'm going to put a 2 in front of the ammonia to now have 6 hydrogens over here. So we're going to do this in pencil. And so, because 2 times 3 is 6, and now I have 2 N's, 2 times 1 is 2. I want to get 6 hydrogens over here now. So I'm going to put a 3 in front. 3 times 2 is now 6 hydrogens, and 3 times the 1 oxygen will get me 1 oxygen. So I'm good. But I messed up the nitrogens over here. There's 2 nitrogens on this side and only 1 on this side. So let's put a 2 in front. Now I have 2 nitrogens. So you're going to see we're going to have to go back and forth. So I always balance these with erasers. Okay, so I always use a pencil because I'm usually going to have to go back and do something else. So now on the right-hand side here, or the left-hand side, sorry, I can tell my right from my left on my laptop. I have 2 oxygens on this side. On this side, I'm going to be really careful. I have 2 times 1, 2 O's for here, and 3 times 1 for 3 O's over here. So I have a total of 5 oxygens on the right. Now, how am I supposed to get 2 into 5? Now, there's a couple ways you can do this. You can use a fraction. Now, a lot of people hate fractions. When I was balancing equations first time out, I hated them. But they are an easy way to get this done right now. Now what you can do is you can use a fraction and give me the number of oxygens you want in the upstairs of the fraction and divide it by the number on the subscript of the element you're talking about. So what is the subscript on oxygen? So in this case, the subscript on oxygen is the 2, and the number that I want of oxygen is 5. So if you put 5 halves over here, 5 halves of a mole, or if you want to say that's 2.5, that's fine, 2.5 moles. If you take 5 halves times the subscript of 2 there, because remember a coefficient is always multiplied through by the subscript, the 2's would cancel and that would get you 5 O's on the left. So you could have a 2, 5 halves, a 2, and a 3 as your coefficients, and this thing would be balanced. I'm going to get my eraser out here. Now the other thing you can do is if you hate fractions, which I always did, so let's get rid of that fraction right there. At this point, when you realize that you might need a fraction, what you can do is you can go back and instead of having whatever coefficient you have out now, right now we have a 2 and a 2 and a 3, double the amount you have. So instead now have 4 ammonias plus the O2. And we're going to double this, so we're going to have 4 NOs plus 6 waters. So 2 times the 3. So double everything that you have thus far. So now we have 4 nitrogens on this side. We have 4 nitrogens on this side. We have 4 times 3, or 12 hydrogens on this side. We have 6 times 2, or 12 hydrogens on this side. Now let's see how many oxygens there are on the right. 4 times 1, so 4 oxygens here in the NO, and 6 times 1 for the oxygens in the water, so 6 O's there, for a total of 10 oxygens on the right side. So what coefficient do you have to stick out in front of O2? So what number times the 2 subscript gets you 10? Yeah, 5. So if you run into a time where you're looking and you're like, oh no, I need to use a fraction, you can either use the fraction like this, what do you want over what is your subscript on that particular element, or double all your coefficients and start balancing your reaction over. Now if it doesn't balance, then go back and triple all the coefficients and go back and try to balance your equation. Okay? So here's our balanced reaction without fractions. Otherwise this would have been, let's look at, oops, I don't want my highlighter, I want my eraser. With the fractions, this would have been a 2 coefficient, a 5 halves, a 2, and a 3. That is also balanced. Or you could have said 2, 2.5, 2, and 3. Either one. So let's balance this guy. All right, take the most complicated molecule on the left and balance. There are 2 carbons on this side. Let's put 2 on this side. There are 5 and 1, so 6 hydrogens on this side. So we need 6 over here, so put a 3 in front of the waters. 3 times 2 is 6. Now on this side, there is 1 oxygen here, don't forget it, and 2 here. So there's 3 oxygens on the left. There is 2 times 2, okay, because there's 2 CO2 molecules over on the right-hand side, guys. So if you have to write them both out and see, there's 2 oxygens and 2 oxygens for 4. And there's 3 times 1 for 3 over here. So we have a total of 7 oxygens on the right. Whoa, 3 is not going to go into 7. So what we can do is we can look at how to get these things balanced. Now, what I can do is I can, first of all, see if there's anything I can do to the left. For example, I've got 1 oxygen here and 2 here. But if I were to put a 3 in front of this O2, 3 times 2, I would get 6 oxygens here, plus the 1, which would get me 7. So this would get me balanced. So if I did that, I've got 1 oxygen here, I've got 6 oxygens there, and I've got, for a total of 7 on this side and 7 on this side. And then she would be balanced. So balancing reactions, the funness that is here. So if we were to look at the very top one here and go through and balance it, I have 3 carbons on the left. Let's put 3 carbons on the right. I have 8 hydrogens on the left. Let's get 8 over here. So 4 times 2 is 8. I have 2 oxygens on the left right now. Let's count them up. 3 times 2 is 6. And 4 times 1 is 4. So there's 10 oxygens on this side. So just put a 5 there and we're balanced. Always pick the most complicated molecule first. Let's look at the second one. The second one, there are 4 borons on the left. So if we put a 2 here, 2 times 2 is 4. There is 10 H's on the left. So if we put a 5 here, 5 times 2 is 10. And then there are 2 oxygens originally on the left. Let's look on the right. 2 times 3 is 6. 5 times 1 is 5. So we have 11 O's on this side. Now I need 11 O's then in order for us to look at balancing this guy. So I need 11 O's. So I can do 11 halves. Okay, 11 halves. What I want upstairs, the subscript in the basement. Okay, so I can balance it with 11 halves, or I could put 5.5 in there, 5.5. 5.5 times 2 is 11. Okay, or what I can do is let's take the eraser here and let's erase the stuff underneath. So this is balanced right now with a fraction. Now, if you don't like fractions, go back and put a 2 in the beginning complicated molecule and double your coefficients that you've written down thus far. And what you would notice then is that we're going to end up over here with 22 O's on the left. So if we took 11 times 2, we're going to get 22 on the left here and 22 on the right. So we would have a 2, 11, 4, and 10. So if you hate fractions, this is what you would have there. Now let's look at number 3. Now number 3 involves a couple of things. First of all, this NO3 gift basket, the polyatomic ion, is present on both the product and reactant side. And this is the most complicated molecule, the lead nitrate. But you're going to notice the nitrate is found in the product. So you're going to notice over on the left here that there are 2 nitrates. Okay, so we can look at balancing the whole package here if we want. Now there's 1 lead on the left, 1 on the right. There's 2 nitrates on the left, so let's put a 2 in front to say we want 2 of this entire nitrate group. So it's like writing down the KNO3 molecule, or excuse me, unit formula, formula unit down twice. So there's an NO3 group and an NO3 group. So there's 2 of them on the right now. So that's balanced on the left. There's 1 Ki on the left, and now we've changed that, so there's 2 Ks on the right. So let's put a 2 in front of potassium. Now we have 2 potassiums. There's also 2 iodines on the left, and there's 2 on the right. So this is now balanced. Oh, the next one is ugly. So let's just look at, first of all, the first one on the left here. They're both complicated. The PO4 does appear on the product and the reactant side. And so let's balance this baby. So there is 3 sodiums on the left. Let's put 3 on the right. There's 1 PO4 group on the left, and there are 2 on the right. Okay, see the 2 outside the parentheses? It means 2 of the PO4s. So in order to get 2 PO4s, I got to put a 2 out front on the left. I just messed up my sodiums. So I'm going to get my eraser here. And so I have right now 2 times 3 sodiums, or 6. So I'm going to change that over here to a 6. And I have 2 times the entire PO4 group, because I have 2 PO4s on the right. Let's go to the next molecule then. I have 1 calcium here. I have 3 calciums over here. So let's put a 3 in front. Now we have 3 calciums. I have 3 now. And then we have the nitrates, which have 2 in each of the molecules. So 3 times 2 is 6 of the nitrates on the left. 6 times the nitrate group gets me 6 nitrates on the right. Woohoo! We're balanced. And the last one. Well, there's only one thing on the left, so we're going to start with that. 1 nitrogen, 2 nitrogens. Put a 2 out front. So we got 2 nitrogens on the left. So 2 times the chlorine here. So 2 times 3 is 6. So we just need a 3 out front to get 6 of the chlorines. Woohoo! Now, I do suggest Google balancing chemical reactions and do tons of these. They do get more complicated. You do need to be able to balance an equation in a minute or less, okay? Because we utilize these ratios then. For every 1 propane, we would use 5 oxygens to make 3 carbon dioxides and 4 waters. This is our recipe. The recipe is the most important formula. Of course, if you're going to want to make a new cancer drug or Post-it note glue or a new clean gasoline, we need to know what ingredients we're going to throw in, or chocolate chip cookies. What ingredients we need to throw into the bowl to make the chocolate chip cookies. If you don't have a recipe and you just let a 5-year-old loose in your kitchen with a whole bunch of ingredients, they're not going to know what to put in that bowl. You might have soap in with some water, in with some milk, in some with some grape Kool-Aid, in with some Rice Krispies, you know, in attempts to make chocolate chip cookies. So you need a recipe in order to read and instruct someone how to make the product. Now you'll see on the next slide here, this is 11 halves. Okay, you don't have that. There was a typo here. It didn't. Looks like 1.5. Should be 11 halves here. But here are all our answers filled in. Now, we are omitting section 3.11 on organic compounds. You don't need to know this in Chem 139. We will introduce organic compounds, and those are things that usually are combined with carbon-based, mainly carbon, and then sometimes they have some hydrogens, oxygens, and nitrogens in them. But we're going to ignore those for now and come back to them then when we get you into Chem 161. Okay, that's it for chapter 3. Only one more chapter left. I'm glad that you joined me for the video. And if you find any mistakes or other typos, please get a hold of me.